The continuation of infrared radiation from objects. Sample problem. We have a block, it's a cube of side length L. It has 6 faces, top, bottom, right, left, front, and back. We don't specify its temperature. We don't even specify its area. But we do specify that its rate at which it's emitting radiation is 12,000 watts. And we'll record the fact that A1, the area in the first case, there'll be a second area soon, is 6 times whatever the area of one face is, which is the area of a square, L squared. 6 of those gives the total area. Now we slice through this cube, creating 2 equal blocks. That one slice adds the inside cut area on the left and the inside on the right, adding 2 more faces that will radiate or that will contribute to the overall area, total area of this object radiating IR. So the new area will be what you used to have, 6L squared, plus 2 more of those squares, double L squared, for a total of 8L squared. Now, we write down the expression for R1 here, following the usual pattern for calculating rates, where we use A1 as the area, substituting from here. A1 becomes in the parentheses 6L squared, and I'll pull that 6 out front. And now we'll do the same sort of thing for R2. It's sigma E times its area, which is 8L squared, times the Kelvin temperature of the 4th power. I pull the 8 out front and have 8 times this. Compare that to 6 times the same thing. Well, now let's construct the ratio of R2 to R1. R2 over R1. R2 is 8 times the parentheses. R1 is 6 times the parentheses. The parentheses are identical, and so they cancel, leaving behind the fraction 8/6. Now we take this equation, R2 over R1 equals 8/6, and rewrite it this way. R2 is 8/6 times R1, but R1 is 12,000. 6 into 12 is double, times 8 gives a total of 16,000 watts. 16,000 watts from this block. You might want to try on your own answering the following question. What if we cut it twice, made 2 cuts? Well, here's the rule. Each cut adds 2 faces. So if you cut twice, you will have added a total of 4 faces, and so on. Well, I think we've seen enough of this example problem. There will be more discussion in the next part dealing with infrared radiation. When we come back next time, what we'll do is put an object in water or any other fluid, such as air, and be told that 2 things are occurring. The object is radiating IR to its environment, into the space surrounding it, never to be seen again by that object, but all other objects in this object's environment are likewise radiating IR. And some of that IR is absorbed by that original object, which would tend to warm up the object while it's attempting to cool down as it radiates its energy. So we ask the following question. What is the net rate of loss of energy through not only emission from itself, but also taking into account absorption? So there's a loss on the one hand by emission and a gain on the other hand by absorption. How do we handle that sort of situation? That's the question I'll answer next time. See you then.